Hello and welcome. Let's talk about type variance. This is a concept specifically related to generics that help you understand the relationship between objects and the types inside those objects. So the concept of variance describes how types with the same base type and different type arguments relate to each other. So we know from the collection classes that they take generics. Right? You can specify a list for the base type, and then inside the angle brackets, you can specify different type arguments, string or an any. Well, how is string and any? How is that related? And how does that work in terms of that generic class? How are things related? How can you use it? So if we consider a class called Apple, this is a more real-world practical example. If you have this class Apple and you have a subtype of that apple called fruit, a subclass, then if you create something like a crate that takes an apple, and you have a crate that's a fruit, is an apple, a crate an apple, a subtype of a crate of fruit? That's the question you have to understand. You have to understand this relationship. Just because you have this container, this class that takes specific parameter types, if those parameter types are related, how are they related? What can you do? So in this example with a crate and an apple and a crate of fruit, even though apple is a subtype of fruit, a crate apple is not a subtype of a crate fruit for the most part. So a crate apple can be a subtype of crate fruit if it's a supertype of it, or neither, depending on which type of variance is used. So there are different types of variance. But the concept of variance is this question: how are the type parameters related? Just because one type parameter is a subclass of another type parameter, does that make the entire class a subclass of the other one? Is crate apple a subtype of crate fruit? So it depends on what type of variance you're doing, and it also will affect your implementation. So understanding variance is essential when you write your own generic classes or your own generic functions. If you don't write your own generic classes or functions, you can ignore variance. It helps you create APIs that don't restrict users in inconvenient ways and don't break their type safety expectations. So type safety is all this concept of whether or not you have to cast, whether or not you can do certain operations on certain types. If you don't understand variance and don't implement your classes correctly that are generic or functions that are generic, then you're going to force your users to either typecast or they're going to have to do all these inconvenience things. You want to make your classes, they're your API, your interface, you want to make them as easily accessible and usable as possible. So you need to understand variance. Let's talk about invariance. A generic class is called invariant if for any two different types, A and B, some class of type with type parameter A isn't a subtype of or a supertype of some class of B. That means there's really no relationship between those parameter types. In Java, all classes are invariant. If you have a list of strings or a list of ints, it doesn't matter. They're invariant. There's no relationship there, even if the ints are a subclass of strings, even though in that case they're not. So there's no case in Java where you have any kind of variance, covariance, or contravariance, which we'll talk about in a second. So crate and apple might not be a subtype of crate fruit. In Kotlin, type parameters are invariant by default. There is no subtype relationship between the types. So by default, it doesn't mean they're always going to be that way, but by default, that's how they are. So if you have a type M with angle bracket type parameter T, it's neither a subtype nor a supertype of M angle brackets U. Regardless of the relationship between T and U, by default, in Kotlin, everything is invariant. You have to use specific keywords if you want to make those things relatable to either be covariant or contravariant. So if you don't use those keywords, it's going to be no relationship for the subtypes. So to the compiler, a crate of apples and a crate of fruit are as related as a crate of apple and a crate of big decimals. No relation. That's invariance. Memorize that. Covariance is when you have a generic class, two different types A and B, and A is a subtype of class B if A is a subtype of B. They have that relationship. So for example, if you have class producer and the type is a cat that's being passed to, and cat is a subtype of a producer animal, that means it's covariant because cat is a subtype of animal. You identify the relationship of those generic types. And if those generic types have a relationship of subtypes, subclasses, then that means the generic class is covariant. To declare the class to be covariant on a certain type parameter, you have to use the out keyword. Because remember, by default, they're going to be invariant. If you want that relationship to exist, you have to use that out keyword before the name of the type parameter. So this below class here is a covariant on T. Here we have our interface producer out T. And we're saying that any subtypes that have that subtype relationship, that class producer, that generic class producer is going to be covariant. So here we have a simple function produce inside there. This is a covariant generic class. Making a type parameter of a class as covariant makes it possible to pass values of that class as function parameters and return values when the type arguments don't exactly match the ones in the definition. So there's more flexibility when you have a covariant class. You can return things differently as long as they don't match. It makes it more reusable. You can't make any class covariant. It would be unsafe, right? If you don't have that relationship, you don't want to just go blanketly making everything covariant. It constrains the possible uses of this type parameter in the class, so you have to be careful. To guarantee type safety, it can be used only in so-called out positions, and that's why we use the out keyword. The out keyword has specific meaning. The class can give out values of type T but not take them in. So for example, a class that declares a type parameter T and contains a function that uses T, if T is used as a return type of a function, it's in an out position. It's returning it. The function produces the output. That's what you got to kind of think of. Function produces output values of type T. And we'll get to an example in a second. Contravariance is the opposite of covariance. A generic class is called contravariant if the relationship between any of the type parameters is reversed in the types themselves. So for example, string is a subtype of any. Box string would be a supertype of box any if a box had its type parameter marked as contravariant. The opposite. String would be a supertype of box any. When you want to mark a class as a generic class as contravariant, you use the in keyword. And that has specific meaning as well. So you would just say interface generator. Right before the type parameter, you would use the in keyword. So for example, a class that declares a type parameter T and contains a function that uses T, if T is used as the type of the function parameter, it's in the in position. The function consumes the values of type T. You're not returning it. It uses those values. So here is a table describing these relationships and these concepts of variance. Invariance, contravariant, and covariant. Covariant. If you have a producer, the way that you specify it, use the out keyword right before the generic type. This is where the subclassing for the class is preserved. Producer cat is a subtype of producer animal. You can only use T in out positions when you return data. If it's contravariant, you specify the in keyword right before the generic type, and the subtyping is reversed. Consumer animal is a subtype of consumer cat. You only use that in positions for parameters passed in to the generic. You don't return it. For invariant, there's no subtyping. T can be used as a return value or use the parameter and operate on it and do whatever you want. Related to variance is this concept of a covariant return. This is when you can return subclasses and so forth. So here we have a base class called animal. We have two subclasses called sheep and frog of animal. And then we have another class called farm. This has a abstract function called get, which returns an animal. And then we have another abstract class called sheep farm, which is a subclass of farm. That overrides function get. So this inheritance hierarchy looks like animal at the top, sheep and frog below it, and then farm by itself and sheep farm, a subclass of farm. So we have a hierarchy of animals. Our generic farm just returns an animal. In Kotlin, it is fine for more specific sheep farm to return a sheep. That's covariant return. So when this function is invoked, the type of the compiler and for the return value will depend on the type of the farm variable itself. We can return a sheep inside our sheep farm, even though sheep farm is a subclass of farm, which has returning a subclass of animal in its get. So we can do something like this. We can say a variable farm of type farm equals sheep farm, right? You see this often in when you're trying to do something polymorphically. You can call get on it. Get of farm is going to return an animal. And then you can also call sheep farm, create a new sheep farm instance, and call get on that. And that can also return a sheep, which is a subtype of animal. So the animal1 variable is only of type animal, whereas the animal2 variable is of type sheep. So you can have two different return types for these functions. Farm.get, again, is going to call sheep farm. There's no implementation there, and it's going to be a covariant return. So to summarize, because these concepts you got to kind of memorize, and I'll provide some examples. Variance is a way to specify how type parameters are related. A type can be substituted for its subclass or its superclass. You can declare a class as covariant on a type parameter if the parameter used is only in outpositions, return values. The opposite is true for contravariant cases. You can declare a class as contravariant on a type parameter if it's used for only in positions. The read-only interface list in Kotlin is declared as covariant, which means list string is a subtype of list any. And if it's covariant, it can be used in the out position, and you can return a string for any. The function interface is declared as contravariant on its first type parameter and covariant on its second, which makes animal int a subtype of cat number in our previous example of contravariant. So let's bring up IntelliJ and look at some examples. First, let's look at an example of why variance exists. Here we have a function, print contents. It has a list name parameter. It takes type list of any. This is not a generic. And we call list.join2string. And this could be any type. Now in our main routine, if we call this, if we call print contents with a list of strings, this is going to work okay because by default, this is invariant. There's no relationship, but we're not using generics. And so the list class is covariant, so this is okay. So if we run this, we see ABC and BAC will display. We're able to join the contents on that. Because this print contents takes a list. A list class is covariant, meaning that it's defined with the out parameter and it has any, and list any is a base class of list string. So you can return list.join2string can return a string even though it's a subclass of any. And that's why that works. Let's create a generic function that is covariant that copies some data. So we can create a covariant function, copy data, by specifying. So let's create a function that is a generic but doesn't have any relationship. By default, this would be invariant. And so what we're doing here is we're copying data. We have bounded parameters. We have constraints. We're saying that our type has to be a subclass of R, and also it can be of type R. That's inside, and we're taking a second parameter of R. So there's two parameters that this can take, either a subclass of R or R. And our first parameter is going to be T. Our second parameter is going to take the second type, the destination. And we're going to go through all the items in the source. For item in source, item is just going to represent the element inside the mutable list. And it's going to then call destination.addItem. And so this is invariant, so there's no relationship. And we can use this in the following way. We can create a mutable list of 1, 2, and 3 of ints and a mutable list of any items. We can say copy data ints to any items and then print out any items. So here we're going to print out 1, 2, 3. We're copying the ints to the mutable list of any. Right? So this is invariant. There's no relationship here. It's saying that it's perfectly fine to copy that. You're adding elements to the destination. We're not using this as an out, as a return value. We're more or less using it as an in, but we're just adding it to the list. Now let's look at it using the out keyword to make it covariant. Here we're going to create our copy data, but we're going to use the keyword out so that we're going to specify that we can only return this. So here we have copy data. We specify that the source has to be a covariant relationship. The destination can be whatever. So now we're going to call it in the same way. We're going to create an int, create an any, and we're going to add to the any. So when we run this, it's going to work because we're using output on our any type. So we're still able to do destination.add. This is mainly because of the parameter specifying as out. Now let's use the in keyword and just use the parameter inside the function. Right? Our source is our ints. And so ints is our source. We're not modifying that. That's why any works. We can specify contravariant by using the in keyword and also calling it a little differently. So our destination parameter now that takes a generic type has the in keyword because we're going to use the input as a parameter. So here we're going to call it creating our ints, creating our any items, and then copy data ints to any items. And here you see it work as well. So this is how you can show relationships. You'll want to play around with these examples and change the way you're copying the data to see some of the differences. But it's important to understand those types for those containers, how they're related, whether they're covariant, invariant, or contravariant. Thank you.